So, and in spite of that, I promised to talk about cost constraints optimal designs. It's a little bit different from what, say, we described with Sergey in our book, when cost, it was actually to some extent penalties. For instance, if you allocate patients to some kind of bad doses, which can cause some harm to your patient, or which are not effective at all, not efficient at all. So it's a little bit different, and I will mainly talk about operational costs, which are quite different thing in this particular, in any actual setting. So, and I start with this very simple but ugly enough model, because it's so many notations and everyone saw similar notations, and I want to be sure that I will not use gamma where Sergey used theta, or other way around, so not to confuse everyone here. So I start with very simple model, linear model, and only one thing I do not, unlike few people here, I do not introduce effects which are not random. All effects in my case random, and they have just, you see, if gamma have normal distribution, I believe it's some kind of gamma 0, its mean, and there is some variance covariance matrix of this distribution. Right? Does it work? Okay. It worked with others. I will follow example of what is that? Okay, so, and in this case, I just do very standard assumptions. And what I actually assume, unlike many people who made presentation very recently, today, I mean, that there are opportunity to repeat your observations at given dose. So when you have one patient, you cannot do, you can, but it's not very useful, and it's first remark. The second, you cannot actually use, you see, to restore, for instance, dose response curve, you cannot use observation dose 1, dose 2, dose 3, dose 3 without some additional assumptions. So you have to exclude all these memory effects, and you have to really be careful. And so my major object, just for the sake of simplicity, will be only one object, and it's so-called multi-center clinical trials. So in these clinical trials, what I can do, my observational unit is a center. Clinical center or clinical site, as they call. And in this clinical site, I can have number of subjects, but I do not consider variability between subjects. I only consider variability between centers or sites. So I can use in one site, say, 5 subjects on dose 1, 10 subjects on dose 2, and so on. So my dose response curve is specific to some extent for this site. So, and side effect, I consider it's random. And we try to consider very similar problem with Byron Jones, and it was quite a while ago, and then somehow it was, I can't say forgotten, but just looks like nobody interested, in spite we published it, so probably nobody even read this paper. It was there is a reference at the bottom, and so, and to a very large extent, I do this presentation and use this notation. I follow results in our, Sergey, I do not remember what chapter is it, in our book, and for the same reason, I assume nobody read this chapter, so it will be useful to repeat what is to describe what is done in this chapter. So, and to a very large extent, what I follow, it's follow very efficient way, recycling. So, and in this case, it's to some extent recycling of relatively old ideas. So, and we will see, is it useful or not? So, it looks like a lot of people believe in recycling, so I believe in this too. So, is it impressive, but extremely boring? And so, it's basically notation, but the basic idea, to be a little bit faster than before, what I consider quadratic deviations, that's all, my observation from model. And you can, I assume for the sake of simplicity, so y could be vector, but let's assume that they are uncorrelated responses. Otherwise, it's additional notation, and it just doesn't change too much. Now, for the sake of, how many times I said for the sake of simplicity? So I try to simplify everything, but I assume that population variability omega is known, because if it's not known, actually it's much more difficult, and a lot of people discuss that it's caused some kind of problems. So, but to understand what I'm for, I will assume that just it's known. And then some of squared deviations can be nicely partitioned, as people do usually. And so there are, say, gamma I, it means it's in I side we have this specific gamma, of course, which we do not know. Then at each side I have observations, and these observations can be expressed in this way. So either this way or that way. Look at definition of, gamma with cap. Gamma with cap is just usual least square estimate. I do not do any assumptions about shape of distribution. I do assumptions about mean and variance, period. It's a very simple approach, maybe not most effective, but in most cases it's quite effective. And all results are actually were known for quite a while. I think it was one of pivotal papers in the 60s, and so I think Raut published a few papers in this direction. And actually I enjoy reading this survey paper by Spotwell. I'm not sure that I pronounce this name correctly, but there are some people from Scandinavia, so you can correct me. And really results are very simple, looks very simple. What is crucial here? There are some estimators for in each site. So I estimate these parameters of those response curve. And I assume you probably notice that I can invert information. I call it information matrix. It's not information matrix, it's not Fisher information matrix. It's actually matrix which inverts to some kind of variance. So it's inverted variance covariance matrix, or in design of experimenting all the times it's called moment matrix, matrix MI, which is inverse of variance covariance matrix. So here there is no approximation. Everything so far is exact. So now I have another class of observation, secondary observations, gamma with bar and subscript I. So this is some kind of, you see, shrinkage estimator, which friends cited today. And those who are Bayesians, they can view them as some kind of Bayesian estimator, if you wish. And here there is nice connection between, say, Bayesian approach. And I don't like this separation Bayesian and frequency. There is just good approach and bad approach or whatever. Bayesian and frequentist approach. I think you have to apply what you needed at that point. So actually, when you know this gamma 0, and Bayesians assume that they know, well, go ahead. If you know, you can use this formula. It's not a big deal. If you do not know, you have probably to estimate this. So that. Okay, let us move. If there is, and definition of design. Now, what is design? I have design at each site, so it's number of repetition at each given dose. So again, I have opportunity to do repeated observation at each dose. It's not what you are doing in PKPD. You cannot repeat them. Now the second definition, so will be on the next slide, by the way.
So can I ask a question?
Well, sure, I will.
Assumptions on the center effect that it's a
So I assume
sample from a population, or
you see in each sample I enroll given number of patients. And what I'm trying to say, if at this site or center, say in Russia, those responses could be of one shape. If it's, say, south of United States, those responses could be slightly different across this subjects associated with this particular site. So all randomness is coming through difference, I mean the second level randomness coming through that we are moving from one side to another side, not from one subject to another subject.
I'm just trying to see if you're assuming that there's a population and these are randomly drawn from a population.
Oh, yeah, sure.
The centers.
You can assume this. It's never this way, but
Yeah,
theoretically,
I was going to say
yeah.
it's never that way.
Yeah, so, but theoretically,
You
yeah,
are
they are randomly sampled. Okay, now what we can so consider here. Here actually there is two variance covariance matrices which it should be somewhere -1 here, sorry. Yes, should be -1. So one matrix is variance covariance matrix of usual least square estimate, and nothing new. So it's nice, and it can be expressed very simple in this way for this linear model. Nothing new. The second is variance covariance matrix, but now I do some kind of additional averaging with respect to gamma, because gamma is entering this shape. And then variance covariance matrix will be inverse of that. So immediately we have two problems, design problems which we can address. Either I minimize the variance of usual least square estimator in the given site or center, or I try to find out optimal designs which actually minimize this Bayesian type of variance. So they are different. The first one is trivial in the sense, if you know experimental design, it's nothing new here. It doesn't depend, if you are talking about continuous design, it doesn't depend upon number of observations. Unfortunately, in the second case, we have dependence of optimal designs from number of observations. And it's actually not very good, because you have to do your exercise for any number of theoretically. Maybe they will all coincide, but they may be different from different number of subjects in each site. So, but still, design problem here is trivial. I mean, trivial in the sense of computation. So it's everything known, and nobody, I hope, will ask any questions here. Now, but what we are interested in estimation of population parameters, which are gamma 0. So that is important for us. How this, if we are talking about drug. So, and here there is relatively simple formula which actually follows least square estimators, some kind of generalized version of that, which is relatively simple, and variance covariance matrix, I emphasize again, so I know exact expression for variance covariance matrix. I don't need information matrix so far. I work with moment matrix, which is not Fisher information matrix, but has the same structure. So, and here I have really, I knew the variance of this estimated gamma 0, estimator of gamma 0. Of course, if I know omega, if I know population variability. So everything looks easy. Now I introduce another design. Now I use this Xi capital. And this design tells me the following one. So I have this Xi I designs associated with site I. And I can use the same design, say 2 doses or 3 doses, in one subset of sites, and another design on another subset of sites, when it can be reasonable, by the way. very often we cannot do multiple doses in one site because people say it's too complicated from operational point of view. Our guys are not that smart as you statisticians. We need 2-3 doses, 2-3 arms in this site. And then you have actually this matrix will be singular. I don't use any complications here, but then that's why when actually different designs can appear in our setting. So it could be, say, 2 doses, minimum, maximum dose in one site, and 2 interim doses in another set of sites. Is it okay? Now, and here, as soon as we introduce this design, which now described by pi I, it's fraction of sites with this particular design xi I, we have standard optimization, again some optimization problem. But now we have to select xi lowercase and this xi capital. So it became a little bit more tedious, and I think Mentre doing it for quite a number of years. And friends, you probably know this better than myself. So this problem is not very good numerically. So it's quite a headache to really to find out solution. But to convey my major idea, I will go to the simplest case when actually I will assume that I use the same design in all sites. So simple-minded guys, I use the same design, 1, 2, 3, 4, many, as Sergey said. So doses, and we'll run. In this case, I can rewrite everything what I am doing in a very simple manner. So I have total number of observation, total number of sites. It's n capital. Is it n capital? Yeah, n capital. Then I have number of subjects in at each site R. And then, after some arithmetic, I have to do this type of optimization. So I have to minimize this criteria psi, which could be D criterion, whatever, with respect to xi. Now it's xi in each site, so it's easy. For each site, it's easy to find. But immediately, I can notice it, and I have to confess, I do not know how to do it in simple manner for D criterion. It's unusual. Usually everything is simple for D criterion. Now everything is simple for linear criterion. So if my utility matrix A, then everything for linear criterion happen to be similar. If you look here, trace is linear operators, and it will be sum of traces, and immediately my optimal design problem reduced to optimization, this stuff. But we notice here that I can do it for any R and N, but there is no constraint. They are just given. But as soon as I introduce some constraint, some cost function, for instance, I introduce 2 cost function. That cost is proportional number of sites and times number of patients is cost of one patient or one subject. And I assume that it's equal to 1. That's why there is no multiplicative, nothing multiplier. I multiply here with other Q1 or Q2. So I introduce only cost for opening site. So it's obvious that it doesn't matter which unit, pound, 1,000 pounds I use. So it's not a big deal. So my cost function is very simple. It's too simple to be good, but let's start with this one. Why? Because I do not take into account, say, for how long I'm doing, for instance, my experiment, my trial. And it may play quite significant role. And so if I do some arithmetic, so I can express, so okay, I fix cost. I can express n through Q and R substitute in this formula, and then immediately I can find out optimal number of subjects in each site. It's trivial. Good news. So nothing to do, and if you consider actually after this introduction, of course, nothing changes. I can do again independently can find out optimal design, which does not depend upon N, capital N, R. Life is beautiful. If you do not know some things, you can live very happily. But as soon as you start to learn something, then life became a little bit nastier. So why? For instance, you do enrollment, and design, which I have shown to you, it's well-balanced design. At each site, I have exactly R patients. Only in this case, it's optimal design. I have a given number of subjects on each dose, on each arm. And here are a simple example. So if you do enrollment, which can be modeled as a Poisson process, and you have, say, 50 sites, and you have to enroll 400 patients. If you do not care about balance between all these sites, you have the same lambda, the same Poisson process in each site. But you just do not do anything in the site, you just wait when subjects are coming. Then to enroll given number of subjects, total number, you need what here is, with probability 95%, you need something about 8 months. So with probability, you get this 400. If you start to care about balanced enrollment, that in each site you have exactly given number, it's simplified here. And I think it was done for 2 arms, and then there is also some limits that you have in each site at least 4 patients. Then to get 400 subjects, you need actually almost 20 months. And if you read this sentence at the bottom, so of course it's cheap trick, but you see, people say that if you have a good drug, it brings a lot of money, and in this particular case, you see, each day lost day, it's about, say, 2 plus something millions. So what is better, to enroll instead of 400, enroll 500, and to have unbalance of the trial, but I have 500 instead of needed 400, or to wait when it will be completely biased, completely balanced. So that is a standard question which we have to address. That is what I called operational cost. If I consider revenues here, potential revenues, then optimal designs in classical understanding really doesn't look very optimal. So we have to take into account operational cost. That is crucial. Okay, I can do this. Now, and by the way, there is another thing, that is very old result, by the way. Probably we did it with Byron Jones, somewhere 2005. So we did the following. So let's assume you have very simple model. It could be, actually it was also a mixed effect model, but you have just simple. You have mu1 and mu2, 2 means, and you have side effect and all that stuff. So if you have really standard situation, no difference between sides, so all sides are equal, then your variance, if you have n patients, will be 4 sigma square divided by n. Everyone who made difference mu1 minus mu2, all those estimates, you can find out this. Now, if you add that there is variability between sites, and this variability described by S square, which is variance of population variance, then immediately you have inflation of your estimators. And I always believe in estimators, not in hypothesis testing, and I explain it why later. So Now, if you introduce that there is treatment effect and random enrollment with all equal enrollment rates, then you have another inflation, this term. Now you assume, you see, it's strong assumption that all sites are equal in the sense of enrollment. They are slightly different. If you model it with some, say, gamma distribution, doesn't matter actually, gamma, so they have some variability of, and this is described by omega square, it's relative, I think it's relative, relative standard deviation of enrollment. Then you have another inflation. So each time you have some inflation because of you have operational variability or uncertainty. And that should be taken into account from the very beginning. And here I work in terms of estimators, so probably for people who like hypothesis testing, you always can connect estimation, because estimation usually sufficient statistics in most cases. Well, so this one, but now there is other nasty thing. So here one nasty thing about this problem. You have to take into account operational cost to build optimal design. You have to define what does it mean. Now, by the way, we plotted some curves. There is curious dependence. So it's actually, for these random effect models, it's important to have relatively large number of, in this case, sites. It's very slowly changing function when you have a large number of units. As soon as you have smaller number of units, increase will be quite substantial. And it's clear, because it will be dominant. You have just, what does it mean you have random model? You observe mu1 in each, or mu2 in each site, say 10 times. You cannot estimate omega very well. So variance, population variance. To estimate population variance, you have to really to have relatively many units. So subjects.
What are the axes and what are the colors?
R, okay, so, okay. You give me 5 minutes. because you see, he needs some explanation and I cannot say no. So R,
2 minutes.
R is revenue, so per month, potential revenue per month. C is the cost of your lambda. So enrollment rate, you see, you increase enrollment rate, say, by opening additional sites, or whatever trick you are doing. So lambda is not given for free. So this is cost, and this is ratio. N capital is number of sites, and in low case is the number of patients. And you can see that actually, and here, combinations when you have variants which satisfy some bound, prescribed, for instance, FDA, whoever. So which satisfy to these alphas and betas, say 1 is 0.05 and power is 0.8. So, and you can reach it with different combinations of sites and patients. And so, and you can see you need 622 when you have 78 sites. Patients to get the same variance, or you need 240 patients when you have 208 sites. So that is, but here there is losses of the function which I have shown you a couple of slides ago. If you're interested, we can chat about it.
So can you tell us what? So it's cap n at the bottom and y-axis is little n.
So y, this is a cost. This is total cost. This is the number of sites. This is the number of sites. So n small with star is defined because I have to satisfy, I have to get variance of my estimator of given value. So it's well-defined problem. So it's, I can find out this, all this relationship between all these three values, variables.
Small n on the vertical axis.
No. Vertical axis is cost. Vertical axis is this function. This function, it's cost. Now, and I have, you see here there is bound on my variance of estimated parameters. This is a bound which depends upon, you remember it was inflation of ta-ta-ta, so. And now it has to be, of course it has to be equal to find out all this. And now you move using this to see, using this one, and this formula, you build this plot. Of course, you can give it, can solve it analytically, but you can also plot these curves. So it's, and it's done for different, actually different prices of a cost of potential revenues. Okay, now actually I have one bad news which I want to describe, 1 minute. And it's probably for people who are doing matrix, information matrix approximation. So now, all this was done for linear model, pure linear model. And you see that there are problems already with linear models, which really separate our problem from classical design, experimental design. Now, when you have, say, nonlinear models, and remember, I do not do maximum likelihood. I work with least squares, with linear estimators in a linear case. Now I will build some quasi-linear estimators because everyone works with nonlinear models. So I introduce this function. Instead of, you see, function x1, x2, x3, whatever, I use these derivatives. Okay? So it's new basis function. So it's new basis function. And what is really, we have to pay attention that when we take derivative, we have to calculate this derivative at the given gamma. And this gamma is different for each subject or site. In our case, site. So it is different for each site. And now when I start to calculate this moment matrix, or information matrix, it's not Fisher, it's information matrix. So now this matrix depends upon gamma y. So it's random. And to my knowledge, what I observed today, nobody mentions that this matrix actually is random. It's not only uncertain, you do not know how gamma is distributed, or whatever price distribution, it's just random, because, and we do not know this gamma. So, but there is one, so we have to replace now, you see, in linear case, it was no randomness. It was dependence only upon design. And when we move to nonlinear case, some randomness appears. So, but there is good news. This randomness is coming through some kind of sum. If you look, I sum up information matrices, or inverse of these information matrices. I sum them up. And if we recall some results, so from mathematical statistics, which probably all of us learned quite a while ago, so nevertheless there is still, say, either we can use just law of large number, or in this case actually we can handle even central limit theorem. We can really see that this sum actually will converge, not this sum, previous sum which was on the previous slide, this sum will converge to expectation. So that is sum of expectation. So it's usual just the law of large numbers. So what we have to do, just pay attention, I have to minimize functional psi determinant or whatever trace, but expectation is inside of this functional. It's not like in Bayesian approach when it's outside. And here there is really great sense, because in our case, information sum of this random information matrices divided by total number of sites will converge to sum of expectation. So it's good approximation of this particular object. And when n tends to infinity, it will coincide with expected, like sum of xi's converge divided by n converge to expected x. It's exactly the same result. So that's why we have to do this problem, not what everyone is doing, by the way. A lot of people do averaging with respect, they call it pseudo-Bayesian. and I always object, and there is big difference, by the way, between this is much better problem. And I try to explain why. So at some point, actually, a few Bayesians try to introduce expectation at that point, before, I can finish right now, so before taking functional. And always I said, no, in this pseudo-Bayesian, as they call this actually some kind of averaging to avoid dependence upon unknown parameters, you cannot do this because you can have, when you do expectation of, and they usually took expectation of m. When you take expectation of m, then singular information matrix may become actually non-singular. And that can cause a lot of problems when you build optimal design. Here it's not the case. You have to take expectation of that, and so you cannot, expectation when it will be singular will be not very good object to work with. And so, okay, do I have some conclusions? Probably I have, but I don't have time. Okay, so, but, oops, I move in the wrong direction. Now, everyone can read and I can relax. So there are a few bad news, but they're not too bad, so we can address them.
Okay, thank you very much. Valerie, are there any additional questions? Yes, thank you.
I suppose you could complicate it a bit more, adding the variability within the site. Right?
Well, I can take 2 levels of hierarchy, I can take 3, 4.
That's right.
If you will ask, well,
Yeah.
see,
And won't that be tractable? Because this looks very complicated already.
I think no.
Yeah.
It's like, you see, it's like when Bayesian say, oh, I have prior distribution, so with parameters theta, 0, and omega, and then I will say, and what kind of information do you have about theta, 0, and omega? I look at Peter, so what is your reaction? Okay, say, stop your blah blah and do something. But it's the same, so of course we can make models more and more complicated, but you remember Chekhov, it's probably some people who read Russian, so he said that brevity is a sister or a sibling of talent, and so in this case I would paraphrase it that simplicity is a sister of talent. So we have to stop at some needed point.
I have one question about the curves that we've discussed.
Uh-huh.
Do you expect the balance between capital N and small n?
No.
Is it something
You see,
expect,
no.
or is it dependent on your choice of sigma and omegas and?
Yeah, it all depends upon. So it was built for the case when we just say total number of sites n capital, total number of subject is this one. If you put constraints on that it's not interesting. It will be only term which depends upon time, your delay of experiment.
Yes?
You have a question?
Yes, well, regarding this picture, I was wondering, you're dealing with the same design each.
At that point, yes. So
If you have only 1.1 individual in the mean side.
yeah, I see your point. Actually, we address this problem in our, it was paper, some statistics, some kind of statistical method in medical research or whatever this journalists call. So there are some formulas which actually allows to write down everything when matrices, this moment matrices are singular. That one. It was also technical report in GSK where beta formula were written, just beta for programming, but you can find out this in this paper. And this is very often case because you cannot really you see, to have too many doses, too many arms in one side. Actually, the similar picture you can find out in slightly different setting in PK/PD modeling. Sergey mentions that in children you cannot do more than 2 sampling and so forth, and it will be singular if you feed PK model. So you have to address this problem, and it can be addressed because of its population model. It's only with population model because we can borrow information from other sites.
Yeah.
Okay.
Last question.
You want me the last question?
Yeah.
Can I see the cost function, the loss function, and this slide with the loss function?
Can you show the cost?
Well, I can. Keep in mind that it's the simplest one.
Yeah.
This one or
The
next one?
next one.
Yes, this one.
So is there an expectation? So isn't cost
There is nothing
random?
random. You see, in here, it's expectation or taken only with respect to operational randomness.
So this is expected cost with respect to the distribution of enrollment times.
Yeah. So, and I have to be more accurate. Actually, what I advocate right now, what we are doing, say, working with average, so risk function or cost function, say, expectation of cost function will be risk function, so it's expectation. And I consider that in modern times it's a little bit outdated approach. Probably we have to talk about if we introduce cost function, then I have to minimize, say, not or whatever, 15, which side you from top or from the bottom look. So you have to really to be sure that with probability 95% your cost will be less than something. Who cares about average cost if tail will be, say, with 20% we will be above, say, it will be skewed observation and usually it's very skewed. And you with 20% you will be top larger than your roof. So nobody will. So I consider that even in design we also do very often, we optimize some average number of subjects. So needed to get something. Especially in sequential design, they paid attention to this a long time ago. You have to really to find out design which provides that this probability 95% number of subjects will be less than something. Because if I compare it with standard design, it's okay. So the standard design, sequential design looks like always better in hypothesis testing setting. I emphasize hypothesis testing setting. But on average, but if you start to talk about probabilities, situation will be much worse for people who do sequential design. And probably there are some, Chris can address this, probably it's familiar topic in sequential design.
Okay, well, I think we're moving to another topic.
Okay, so let us stop. There's always a problem with me, you have to stop me.
Yeah, I know. I'm doing. I know you for. Okay, thank you very much again, Harry.